This episode is brought to you by Cisco Educational Premium. On our last episode on atoms, we were looking at the atomic color, where color arises from atomic level. So let's proceed from there. The human eye can only perceive only a small section of the visible light, while everything else becomes invisible. And come to think of it, why are we only sensitive to visible light? Why this particular region is significant? Is because the first eyes evolved while organisms inhabited underwater environments. This portion of light is transparent in water. Infrared and ultraviolet light, however, renders water somewhat opaque. If the first organisms evolved in sulfur lakes orbiting a neutron star, their eyes might see something like X-rays. How does light form and how does it enable us to perceive color? In the core of the sun, hydrogen nuclei undergo nuclear fusion due to immense pressure, transforming into alpha particles and emitting gamma radiation. This radiation ricochets around the sun, colliding with other hydrogen atoms over thousands of years, losing energy in the process, and ultimately emerges as visible or ultraviolet light. It then reaches Earth. Light can either be absorbed or reflected depending on the material it encounters. This is determined by the nature of material. For example, a blue piece of cloth appears blue because it reflects the blue wavelength of light while absorbing all other wavelengths. Thus, it is every color but blue, since blue is reflected and not absorbed. This is why black materials heat up significantly in the sun. They absorb all light and reflect very little. On the other hand, the opposite is true for white. All of this is referred to as bulk absorption and reflection. When a beam of light interacts with many atoms simultaneously, fact is such as the distance between molecules or how the molecules are organized may affect the colors of light reflected. For instance, snow and ice are both composed of same type of molecules. However, their different arrangement result in snow being white and ice being transparent. Meanwhile, water absorbs minimal light and most of it passes through. One who need to venture deep into the ocean to avoid seeing sunlight. Similarly, consider carbon organizing its atom in a lattice results in diamonds, while arranging them in hexagon produces graphite. So coming back to our initial question, do atoms possess color? From the perspective of bulk reflection, no. The wavelength of light are larger than the size of an individual atom. Thus, color only becomes apparent at larger level. But what about thermal radiation? When you heat something up, the atoms inside start to vigorously collide with each other, releasing photons. Regardless of the substance type, the emitted light will adhere to the same color spectrum. However, once again, this only applies when you have more than one particle. For individual atoms, no color can arise from thermal radiation. Finally, there is gas discharge. By passing electricity through a cloud of atoms, they become excited and release photons. The emission of photons in this scenario can vary in wavelength, resulting in different colors depending on the substance nature. As a result, each element possesses each emission spectrum. These are the colors emitted by hydrogen atoms, and similar patterns exist for atoms and other elements. In conclusion, each chemical element has its distinct color fingerprint defined by its emission spectrum. In a sense, you could consider that as its color. However, in a literal sense, the one we perceive in our everyday life? No. An atom is physically smaller than the wavelength of light, making color non-existent at the atomic level. There are four fundamental forces or interactions in nature: gravity, the weak force, electromagnetism, and the strong force. Gravity is most familiar to us at larger scales, but at the quantum level, the other forces dominate. Electromagnetism is exceptionally stronger than gravity, approximately 10 raised to 37 times, and is responsible for electron-proton attraction in atoms. The question arises: why don't multiple protons in the atomic nuclei repel each other strongly due to electromagnetism? According to Coulomb's law, in a helium atom, the two protons experience a repulsive force of about 90 newtons or 20 pounds, which should cause them to fly apart instantly. However, the reason protons remain bound is the presence of even stronger force called the strong nuclear force. The strong nuclear force is about 100 times stronger than electromagnetism. It operates at the scale of atomic nuclei. This force works differently from electromagnetism, and I know it might be new to most of us. I only came across when I took some of nuclear science courses in college. The fascinating world of quantum chromodynamics reveals how protons and neutrons stay tightly bound within atomic nuclei, resisting the enormous repulsive force of electromagnetism. The strong nuclear force, which is responsible for the binding energy within atomic nuclei, accounts for about 99% of the mass of ordinary objects. This is in contrary to the misconception that Higgs field is the primary contributor. To understand the strong force, we need to explore the combustion of protons and neutrons. They are made up of quarks, fundamental matter particles, and gluon, force particles. A proton contains two up quarks and one down quark. Neutron, on the other hand, contain two down quarks and one up quark. Gluons responsible for keeping quarks together carry a color charge. This is analogous to an electric charge, but function differently and is unrelated to optical colors. The color charge comes in three types: red, green, and blue, which combine to make a neutral white. Color charges need to be balanced to create neutral charges, either through a combination of the three colors or through color anti-color charges. Gluons interact with quarks and bind them together. Quarks and gluons are the only particles affected by a strong force. Gluons serve as the force mediators, similar to photons in electromagnetic interactions. If quarks get too close far apart, the rubber band breaks, but instead of releasing the quarks, the energy required creates a new quark-anti-quark pair called a meson. This confinement principle ensures that free quarks cannot exist, and they are always confined within at least one other quark. Mesons play a crucial role in interaction between protons and neutrons in the nucleus. While the strong nuclear force is weaker than the strong force between the nucleons, it is still much stronger than the electromagnetic repulsion between positively charged protons. This force only acts at very short distances around the diameter of a proton and diminishes rapidly with greater distances, limiting the size of stable atomic nuclei. In summary, the strong nuclear force mediated by mesons keeps protons and neutrons tightly bound together in the atomic nuclei. It works in harmony with the strong force that binds quarks within nucleons. This understanding of the strong force is essential for comprehending the nature of matter and the existence of objects and life as we know it. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. They are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.